Unit G covers two pieces of content for Math 30-1, and so I'm going to do the review in two separate videos. This first video is going to cover rational functions and equations. So first of all, a rational function is considered a rational function because the variable is the denominator. And that has a number of implications for the graph of the rational function. It means that now we need to consider a limited domain. It means we need to consider both vertical and horizontal asymptotes. And in some cases, we also need to consider points of discontinuity. We're going to start with question 1. Question 1 begins with our most basic rational function, which is 1 over x. And what we want to do is describe the transformations from 1 over x to this function, y equals 6 over x plus 7 minus 3. We're also going to determine the domain, range, the asymptotes, and the intercepts without graphing the function on our calculator. So what we should recognize is when we talk about transformations here is where the parameters each go. So our vertical stretch and reflection, which is a, ends up in the numerator. X minus h ends up in the denominator because h always goes where x goes. And then our plus k goes on the outside of the rational. You'll notice that we don't need to worry about b here. Taking care of vertical or horizontal reflections and horizontal stretches is not a part of the curriculum here. And H and K are translations, and it reacts the exact same way as it did in our very first unit. So still vertical stretch and reflection for A, horizontal translation for H. If H is negative, it moves left. If H is positive, it moves right. And then K is our vertical translation, up if it's positive, down if it's negative. They also have implication in terms of our domain and range. Of our original function, this domain is that x cannot equal 0 because we can't have a denominator of 0. What ends up happening when we translate that function is the vertical asymptote ends up moving, which means the domain ends up changing. So the vertical asymptote, the domain are both connected to h. At the same time, this one has a horizontal asymptote at k or at 0. So when I move this vertically, what ends up happening is the horizontal asymptote also moves, which is going to affect our range. So the range and horizontal asymptote in k are all connected. So let's go ahead and do this question then. We can see that our a value is 6. So when we're describing our transformations, that means we would have a stretch because it's a vertical stretch. That would be a stretch about the x-axis, and our stretch factor would be 6. Our h value here is -7. It's x minus a -7. So h is negative, which means it's going to move to the left. So this graph is going to translate 6 units to the left. And we also have a k value of -3. Because it's negative, it moves down. So we are also going 3 units down. So there's the description of the transformations from our base function to our new function. We want to determine the domain, range, asymptotes, and intercepts. So let's start with the domain. Domain is dependent on h. So because this moved 6 units to the left, that means the vertical asymptote moves 6 units to the left, and that affects our domain. Our domain then is going to be the set of all x, such that x cannot equal 6. Otherwise, x is an element of the reals. It also means the equation for our vertical asymptote is at -6. Our range, on the other hand, is connected to the k value. So because it's moved 3 units down, our horizontal asymptote also moves 3 units down. So our range is y cannot equal 3. Otherwise, y is an element of the reals. And our horizontal asymptote has an equation of y equals -3. So we've taken care of domain, range, and asymptotes. The last thing we want to cover is intercepts, and we can do that without graphing. To find the y-intercept, all we do is we set x equal to 0 and evaluate. So y would equal 6 over 0 plus 7 minus 3. That would be 6 over 7 minus 3. 3 is 21 over 7. 6 over 7 minus 21 over 7 is -15 over 7. So our y-intercept is at 0, -15 over 7. X-intercept, Not as friendly, we're going to set y equal to 0 and solve for x. So 0 equals 6 over x plus 7 minus 3. The first thing we need to do in order to isolate x is to add the 3 to both sides. So 3 equals 6 over x plus 7. I'm going to multiply both sides by x minus 7 to get the x out of the denominator. So distributing the 3, we get 3x plus 21 equals 6. And now we just need to isolate here. So we get 3x equals negative 15 when we subtract 21 from both sides. Dividing both sides by 3, x is negative 5. So negative 5, 0 would be our x-intercept. In question 2, we are also going to deal with a rational function in this form. So we're dealing with the transformation form. What we want to do in this one, though, is we want to take the given graph and write the equation. And again, we're going to start with what we talked about in the previous question, understanding that the vertical asymptote is going to be connected to our h. The horizontal asymptote is going to be connected to the k value. Our vertical asymptote here, we can see, it's not the best picture, but it is over 2 units to the right. So our vertical asymptote is at 2, which means our h value is going to be 2. Our horizontal asymptote is happening at y equals 5, so our k value is 5. That means so far, here's what our equation looks like. Y equals a over x minus 2 plus 5. I don't know if there is a stretch here or if there is what that stretch is. So what we're going to do is we're going to take a point that was on the graph and we're going to substitute it in for x and y and solve for a. We can choose any point that is on the graph. I'm going to choose this point right here, which is the point negative 1, 4, and I'm going to substitute for x and y, and then I'm going to solve for a. So 4 equals a over negative 1 minus 2 plus 5. I'm going to subtract 5 from both sides, which gives me negative 1 on the left-hand side. And I'm also going to negative 1 minus 2, put those together, gives us negative 3. Solving for a, I'm going to multiply both sides by negative 3, and we end up with a being positive 3. So there is a vertical stretch here, which we can see just by doing some simple algebra. In the end, I'm going to write the equation, and our equation then would be 3 over x minus 2 plus 5. And you could always put that into your graphing calculator and make sure you get the same picture as we do to the right here. Now, both 1 and 2 deal with the rational functions in the transformation form, which is this form right here. So we would refer to this as the transformation form. The next question that we're going to do still deals with rational functions, but no longer in the transformation form. In question 3, we are looking at a rational function that is of the form of a polynomial over another polynomial, or what we would write as f at x over g at x. So because the rational is in a different form, we analyze it in a different way. Instead of trying to determine what the h value is and what the k value is and how that connects to the vertical asymptotes and so on, what we do in this case is we are going to factor the numerator and the denominator, and we're going to compare the factors in both of them. What actually ends up happening here as well in this form is in some cases we end up with what's called either a point of discontinuity or a hole in the graph. For question 1 and 2, when we have this transformation form, there will be no points of discontinuity. There will be vertical asymptotes and horizontal asymptotes, but no holes in the graph. In y equals f at x over g at x, there is a potential to have a hole in the graph. Now, we need to be careful. We sometimes might have a vertical asymptote. We sometimes might have a hole in the graph. We might have both. We might have neither. So we can have lots of different kinds of analyzing coming out of each of these questions. Let's look at 3a. So we want to find the equation of the vertical asymptote and the horizontal asymptote. We want to find coordinates of the point of discontinuity if there is one, and we want to find the x-intercept. So step 1 for analyzing these questions is to factor. So pretty easy factoring here. 2 numbers that multiply to give me negative 8 and add to give me positive 2 are negative 2 are negative 4 and positive 2. And in the denominator, that doesn't factor. We just leave it as x minus 4. So here's what I notice. I notice and I recognize that I would have a non-permissible value at x equals 4. But look what happens. When I simplify, that denominator disappears. That doesn't mean that our non-permissible value disappears. That implies that we have a hole or a point of discontinuity. And it's literally a point. So the x value of that point comes from the factor itself and from the non-permissible value. So because it was x minus 4, that was both in the numerator and the denominator, the x value of the point of discontinuity will be at the root of that, which is 4. To find the y value of the point of discontinuity, simplify the function. So this function just simplifies into x plus 2, and then take that x value and substitute it into the simplified form. So 4 plus 2 would be 6. Our y value of our hole or a point of discontinuity would be 4, 6. Now notice that there's no other factors remaining in the denominator. So what that means is that this one is going to have no vertical asymptote. The horizontal asymptote comes from comparing the degree of the numerator to the degree of the denominator. Here, because the degree here is 2 and the degree in the denominator is 1, that means the numerator is growing much quicker than the denominator is, which means we would have no horizontal asymptote here as well. Coordinates, okay, done that. And then the last thing is the x-intercept. And the x-intercept always comes from the factor that's remaining in the numerator. So because after we factored and simplified, the factor remaining in the numerator was x plus 2, our x-intercept is going to be at the root of that, which is negative 2. So the coordinates would be negative 2, 0. Factor, simplify. If factors match, we have a point of discontinuity. If we have a factor remaining in the denominator, that's our vertical asymptote. Comparing the degree of the numerator and denominator finds our horizontal asymptote, and the factor remaining in the numerator is our x-intercept. Let's do the same with part B. In part B, we don't have any factoring to do. I can't factor 2x squared. It's a monomial. And I can't factor x squared plus 2. We don't factor the sum of squares. So what ends up happening here, and even if we look at this, this doesn't have any non-permissible values. If we try to set this equal to 0 and solve for x, we'll get no solution. So there is no NPVs here, which automatically means there would be no hole or no point of discontinuity. There is going to be no vertical asymptote. There will, however, be a horizontal asymptote. Because the degree of the numerator is 2, and because the degree of the denominator is 2, what we do is look at our leading coefficients. In this case, our horizontal asymptote would be at 2 over 1, our leading coefficients, which would just be 2. Finally, our x-intercept does come from our factor in the numerator, which the root of that would just be 0. So we have an x-intercept in this case at 0, 0. Finally, let's look at C. Same first step, we're going to factor. In the numerator, we can take out a factor of 2. So we would be left with 2 times x minus 5. In the denominator, two numbers that multiply to give us 20 and add to give us negative 1 are going to be negative 5 and positive 4. Whoops. Let's make that neat. So x plus 4. We can see right away as we are factoring that we do have a matching factor in the numerator and in the denominator. So that tells us right away that we have a point of discontinuity. The x value of that point of discontinuity comes from the root of the matching factor, which in this case would be 5. When I simplify the function, it becomes 2 over x plus 4. So to get the y value, I take my x value of my point of discontinuity, plug it into this simplified form, which would give us 2 over 9. There's our point of discontinuity. We do still have a leftover factor in the denominator. That's going to give us our vertical asymptote. And again, we are going to use the root of that factor. So x equals negative 4 is our vertical asymptote. Our horizontal asymptote here, in this case, we have a degree of 1 in the numerator and a degree of 2 in the denominator, which means our denominator is growing much faster than our numerator. That means that we will have a horizontal asymptote at y is equal to 0. Our x-intercept comes from our remaining factor in the numerator. Notice that in this case, we don't have a remaining factor in the numerator. We just have a factor of 2, but we don't have a factor that has a variable in it. That means we will have no x-intercept, which is fine. It just means that it doesn't cross the x-axis, would actually totally make sense because our horizontal asymptote is at y is equal to 0. So that would make sense that we don't have an x-intercept. In question 4, we're going to follow that same logic, but instead of analyzing the graph, we're going to be taking a given graph and we're going to be writing the equation of the function. So we're kind of doing what we did in number 3, but backwards. So we're starting with what we have. Let's start with our vertical asymptote. In this case, we have a vertical asymptote at x equals positive 3. What that tells me is I have a factor of x minus 3 somewhere in my function. And where that is going to be is in the denominator. Our vertical asymptote comes from our factor left over in the denominator. So I know it's going to be x minus 3 in the denominator. I can see I've got a hole in the graph, and it happens with an x value of 1. So from the point of discontinuity, it happens at x equals 1. That means we must have a factor of x minus 1 somewhere in our function. And that means that it has to be in the numerator and in the denominator because it came from the matching factor. So x minus 1 is going to go up and down. The next thing we're going to look at is our x-intercept, and our x-intercept here is at 5. So at negative 5. Which means we have a factor of x plus 5 somewhere in our function, and it's going to occur in the numerator. That's where our x value comes from. So always when we write an equation, we write it as y equals. So there would be our equation. Now, what's tempting to do is to cross out the x minus 1s and then write the resulting function, but we don't want to do that. We want the original function. So what I'm going to actually do is expand in the numerator. I'm going to get x squared plus 4x minus 5 when I distribute in the numerator, and x squared minus 4x plus 3 in the denominator when I expand. This would be the original function that will give you this graph. We can't really see the horizontal asymptote here, and it really doesn't help us build the equation, so we're not going to worry too much about it. Finally, question 5, we are going to do an application question that has us dealing with, this will cover 2 things. It'll cover an application, and it'll also cover how we solve rational equations. In this one, it's a distance, speed, time question, and we can handle these a few different ways. But with a distance, speed, time question, what's nice is to set up a table. So in this case, it says a person takes the same time to drive as 150 kilometers as it takes a plane to fly this many kilometers. So we're comparing a car to a plane, and we are going to look at 3 things. We're going to look at their distance, their speed, and their time. So we know that the car is driving 150 kilometers. We know that the plane is flying 1,350 kilometers. It says here that x is the speed of the car. So we're going to put x here. And if we read in part A, it says the plane is flying 400 kilometers per hour faster. So I'm going to take that speed of the car and I'm going to add 400, and there's the speed of the plane. Now, I don't know what specifically the time is for the car, but here's what I know. I know time is equal to distance divided by speed. So what I'm going to do is I'm going to write an expression for the time that the car drives by dividing its distance over its speed. And I'm going to do the same thing with the plane. I don't know how long the plane is flying for, but what I want to do is create an expression for the time using the distance and the speed. And notice what that does. Now those are rational expressions, which makes sense because that's what we're dealing with in this section. Now, here's what we know. We know that it takes the same time. So in part B, the equation that we're going to use here would be 150 over x, the time that we are driving, is equal to the time that we are flying. We could solve this algebraically, but what I want to demonstrate is solving graphically, because that's a bigger focus in Math 30-1. So when we solve this graphically, the easiest thing to do is to leave everything as it is. So what I'm going to do is into y1, I'm going to put the left side of the equation. Into y2, I'm going to put the right side of the equation. And what I'm going to do then is look for the intersection point. And more specifically, I'm going to look at the x value of the intersection point. When we solve graphically, we only worry about the x coordinate. So going to the calculator, we're going to go to y equals, clear out anything we have in here. So y1 was the time of the car, which is 150 over x. And then for the plane, 1,350 over, now I need to be careful, I'm going to have to put my denominator in brackets, and it was x plus 400. X plus 400. So we need to put it in brackets. Alternatively, what we can do, oh my goodness, is we can also put it in fraction form. So I'll just maybe show that here. If you hit alpha y equals and then number 1, then you don't have to worry about the brackets in the denominator. So alpha y equals and number 1 makes it so that you don't need to worry about the brackets in the denominator. Okay, I am going to set my window settings here just to make sure that I'm actually looking at a reasonable part of the graph that's going to give me the answer. So x is representing speed here. So speed is going to have to be positive, x minimum be 0. And we're also talking about the speed of a car. So I'm not going to be super outrageous with this. I'll maybe put it at 150. Cars can't really go that fast. Y is representing time. And again, I don't know how long that they are flying for, but I know that time cannot be negative. And I will say, I don't know, let's go see 10 hours. Let's see, I don't know if that'll work or not. So let's go ahead and graph that. So we can see the intersection point, which is nice. That's really all we need to be able to do when we're setting our window, is to be able to see the intersection point. So I'm going to hit shift and then my trace to get to the intersection, enter, 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 and we can see our intersection point happens at x equals 50. At x equals 50. So that would be our solution, x equals 50. So in the context of the problem, this represents the speed of the car. So 50 kilometers per hour is the speed of the car. And if we wanted to know the speed of the plane, it would be 400 plus 50, which obviously is 450 kilometers per hour, and that represents the speed of the plane. So that's one example of a rational application question, and it also demonstrates how we can easily solve rational equations graphically. So that's the first half of the review of Unit G. The second half of the review of Unit G is with function operations and composite functions, and you can find that in the next video.